Welcome to this explainer. Let's just jump right in, shall we? If you've ever wondered how the internet actually manages the sheer, mind-boggling volume of information we throw at it every single second, well, you're in the right place. Today, we're taking a look under the hood at the engine room of modern, data-intensive applications. So, think about this for a second. How exactly do tech giants build databases that can ingest literally millions of writes per second without just completely melting their hard drives? I mean, we're talking about massive online systems surviving an unrelenting avalanche of incoming data. To answer that, we kind of have to rethink how data is physically written to a disk in the first place. Which brings us to Section 1, the High Throughput Challenge. Okay, so for decades, the B tree has been the absolute standard. B trees take your database and break it down into fixed-size pages, usually about 4 kilobytes. When you want to write data, the system has to find that specific page on the disk and overwrite it in place. It's doing random write operations all over the disk. But if we contrast that with log-structured storage, it's a totally different ballgame. This model treats the database as an append-only log broken up into variable-size segments. It never overwrites data. Never. It just tacks the new data right onto the end in this incredibly fast sequential stream. As Martin Klupman points out in our source material, sequential writes are generally much faster than random writes, especially on magnetic spinning disk hard drives. And honestly, even on modern solid-state drives, sequential writes still have a massive advantage. So here is the main takeaway. Transforming chaotic, random writes into smooth, sequential writes is the ultimate secret sauce for unlocking massive write throughput.
Moving on to Section 2, Sorted String Tables Explained. Meet the SS table. It stands for Sorted String Table. This format takes that simple concept of an append-only log we just talked about, but it adds one absolute, unbreakable rule. Every single key-value pair in the segment must be perfectly sorted by its key. It's basically like a dictionary, where every word is in perfect alphabetical order. Plus, each key is only allowed to appear once per merged segment. So why do SS tables completely dominate at scale? Well, because the data is strictly sorted, we don't have to keep a massive memory hogging index of every single key in RAM. Instead, we get to use what's called a sparse index. Imagine you're looking for the key handiwork. If your sparse index gives you the exact disk offsets for handbag and handsome, you instantly know which compressed block to jump to. You just look between them. This saves a ridiculous amount of memory. And because it's sorted, doing range queries, like scanning all transactions from last month, is incredibly fast.
Section 3. Enter the mem table.
Now, you're probably wondering, how on earth do we write data perfectly sorted to a disk when user requests are arriving in completely random, chaotic order, right? Well, when a write comes in, it doesn't actually go straight to the disk. Step 1, it hits an in-memory balanced tree data structure, something like a red-black tree, which we call a mem table. Step 2, since this tree is just hanging out in memory, it can rapidly sort those keys as they arrive. Step 3, once that mem table gets to be a few megabytes in size, boom, it seamlessly flushes out to the disk as a brand new, perfectly sorted SSTable file. And step 4, while that flush is happening, a fresh mem table instantly spins up in memory to buffer the newest writes without dropping a single request.
But hang on a second. Memory is volatile. What if someone trips over the power cord and the server crashes before the mem table flushes? To prevent total data loss, every single write is instantly appended to a separate, unsorted write-ahead log, or wall, right there on the disk. It doesn't need to be sorted. Its literal only job is to restore the mem table if things go sideways. Once the mem table safely becomes an SS table, that portion of the log is just tossed out.
All right, Section 4, Compaction and Merging.
Over time, we run into this problem of overwritten clutter. Because we are only ever appending data, if a user updates their profile picture, say 5 times, we suddenly have 5 different entries scattered across 5 different segments. Or if they delete their account, we don't actually delete the data right away, we write a special deletion marker called a tombstone. So, to stop our hard drives from filling up with all this outdated junk, the database runs background compaction. It merges segments together, keeps only the absolute most recent value, purges the tombstones, and leaves us with beautiful, compacted order. And the way it pulls this off is practically magic. It uses the classic merge-sort algorithm. You've got background threads reading the input files side by side. The system just looks at the first key in each file, grabs the lowest key based on the sort order, and drops it into a brand new output file. It repeats this, basically zipping the files together. And the best part? Because this happens entirely in the background, it never ever interrupts the users who are querying the live database.
Section 5. The LSM Tree Advantage. When you take mem tables, sorted string tables, and that background merge sort compaction and you put them all together, you create an absolute powerhouse of a storage engine. This entire architectural setup is called the log-structured merge tree, or LSM tree. First described by Patrick O'Neill and his team, this concept literally revolutionized how we store data. It's a structure built from the ground up to sustain remarkably high write throughput by utilizing those sequential disk writes and pushing all the heavy lifting to the background.
Let's actually pit the two heavyweights against each other for a second. LSM trees versus B trees. The trade-offs are pretty stark once you look at them. LSM trees are exceptionally fast for writes, thanks to that sequential append-only pattern. B trees, on the other hand, give you consistently fast reads, but they rely on those random in-place overwrites. Also, because B trees leave empty space inside their fixed pages just in case you need to update something later, they get a lot of storage fragmentation. LSM trees rewrite data in bulk, so they have a highly compact storage footprint. Bottom line, if your application is getting hammered with writes, the LSM tree is absolutely your undisputed champion.
Section 6. Databases powering the web.
To really grasp how massive this is, you have to look at the real-world titans built on this framework. Ever since Google dropped their legendary big table paper talking about SSTables and memtables, the industry hasn't looked back. You've got LevelDB and RocksDB acting as insanely fast embedded storage engines. Then you have massive distributed beasts like Apache Cassandra and HBase handling impossible scale for some of the biggest apps on the planet. Even full-text search engines like Lucene, which is what powers Elasticsearch, uses super similar sorted file structure for their search dictionaries. The LSM tree really is the unsung hero powering the apps you're probably using right now. Which brings us to our final thought. We've seen how LSM trees conquer these insane, high-throughput challenges with sequential writes, mem tables, and background compaction. But we have to look ahead, right? As solid-state drives get even faster and running massive in-memory databases becomes cheaper by the day, will the mighty LSM tree continue to reign supreme for write-heavy workloads? Or is there a completely new architectural paradigm waiting in the wings to take the crown? It's definitely something to chew on as you keep exploring the wild world of data architecture. Thanks for tuning into this explainer, and keep learning.